Okay, here's a pretty fun problem from my perspective because I like this stuff. So this is a power distribution problem to your house. So let's say you got a power plant making smoke and it sends out three-phase power. You know, there's three phases, A, B, and C phase. And these go through transformers and such, but eventually they'll take two of these phases for any given subdivision, right? So this is like subdivision, a bunch of houses, a neighborhood subdivision. They might pull off A and B phase, and then they'll run this through a transformer, okay? And there'll be a neutral, and then there'll be A and B. You could call it little a and little b, I guess. And this will be, up here, this will be like 13.2 kilovolts or something. And this will be 240 volts, right? Because 13 kilovolts will hurt you, and 240 volts will hurt you less. And this might be approximately, you know, half an amp, right? Very little coming off of here. But there's other houses, and they're all drawing, you know, half an amp, right? Approximately. And because of this turns ratio, there could be, in here, there could be, you know, 50 amps. There could be 100 times that. There could be 50 amps in here, right? And another house, a neutral and AB phase, and another 100, you know, another 50 amps, right? So half amp here adds up to 1 amp, right? And all these other houses, there could be 100 houses on here, and you end up with a pretty good current on these conductors, maybe 100 amps, right? It would supply 200 houses, right? If it was half an amp per house, it'd be, when you had 200 houses, it'd be 100 amps on the main lines at a high voltage. But then you're peeling off a little bit for each house and then stepping up the current and down the voltage to a safe voltage level. Anyway, that's what happens. Let's see, what else is there to say on that? Okay, so let's look at this right here and solve a little more thorough problem about that. So we've got a transformer. This is the transformer that's on your power pole, right? That's doing the 13.2 angle 0. It's angle 0. We'll talk about this in chapter 10. There's three phases here, and they're all out of phase by 120 degrees, ABC. But between any two phases, there's a maximum volt that's going to be 13.2 kilovolts at the power pole transformer peak. So the 0 is just a reference angle. You know, where is 0? Well, you know, it's here. If you were going to graph these on voltage, you just pick the peak. And you know, the difference between these two is just a sine wave, right? The difference between any two phases is itself another sine wave. Okay, so the maximum difference between these two would be the peak of the resulting sine wave. And then we just call that 0, all right? Because it's a reference. Okay, then we've got a iron core transformer, and then the other side of this transformer coil looks like that, and then we're pulling off, there's a center, what we call a center tap, and then there's these wires which are in your house. And they have some resistance, but not very much. So we'll just say 1, 2, and 1 amp. And then there's loads in your house. Toaster, TV, say 20 amp, ohm, 40 ohm. And then maybe you've got a electrical car or something. This could be 10 amp at 240 volts. So don't want to label everything because it gets crazy, but we've got dots. Okay, I made a center tap, which is not a dot, but there's a dot and a dot. Don't get that confused with the center tap. Okay, there's a voltage here, 120, angle 0 volts. And another voltage here that's out of phase by 180 degrees, so it's 120 angle 0 volts. So it's when this one's going up to 120, the other side's going, at that moment, the other side's going down to 120. So the result is 240 across your big loads, right? Which are tied, your big loads are tied line to line or A to B, and your small loads are tied line to neutral or A to neutral, So these are your toaster and TV and stuff, being driven at 120 volts, and then this is your big loads, your electric car, your spa, your anti-asteroid laser beam that you have in your backyard. If you're a prepper like me, you got to shoot down the asteroids, whatever. Yeah, that's what we got. So we got the I from the power plant being supplied at 13.2 kilovolts. It's kilovolts, and these are just volts because it's being stepped down through this transformer, which has a turns ratio, which we're going to figure out. And there's kind of a trick here. There's several tricks in this problem. One of them is how to represent the turns ratio, because you have this center tap. So the trick is we're gonna say that there's a n turns on this side, and then there's n2 turns on this side, but we're going to break it up into half. So we say half the turns are on this side and half the turns are on that side. So it's 2n, n1 to n2 with this 2 in there. This is not necessarily intuitive, but that's what it is. Or yeah. So just deal with that. We need to label all the branch currents, because that's what we're trying to find. We're trying to find all branch currents in the house. And there was something else we're going to find. That might be it. I think we're going to find I sub P. Yeah. So the branch currents, start labeling these guys. So there's a positive here. Let's call this I1 coming out of the positive, going this way. There's a negative here. Let's call this I3 going that way. It's coming out of the positive I1, and then I3 is going into the negative. There's a branch current in this line here. Hard to say which way it's going. This is more of a guess than the others. Let's guess that, though. So this is I2 going that. We're just guessing that it's going that way. And I4, we've got plus up here and minus down here, so the voltage is higher up on top. A good guess would be this way. Okay. Yeah, so that's all our branch currents that we're going to find. Well, we got another one here. This one's I5, and also kind of guessy-ish. And then I6 this way. All right, so we're going to use mesh current. And this is so messy, it's worth it to redraw this, okay? So center tap, line resistance, this was 1 ohm, 2 ohm, and 1 ohm, 20 ohms and 40 ohms, and my anti-asteroid laser 10 ohms. It's good to be prepared. This is I sub C. Okay, so this is a mesh current. And this is, let's say, going this way, agreeing with I1 direction. Let's call this IA mesh current. And then agreeing with I3 direction, let's call this IB mesh currents. Okay. Let's put our dots in there. Don't want to redraw everything because it gets so crazy. So 120 angle 0 degrees volts. 120 angle 0 degrees volts. Positive, minus, positive, minus. All right. Okay, so these are mesh currents around these 3 meshes on this side. And this is branch currents through every branch. So there's a relationship, okay, where, so let's specify this relationship, where I1 is, it's just IA, right? I1 here is the only thing going through this part of the circuit is just IA. So I1 is IA. I2 is I3, I4. What are all these guys? So I2, where is it? I2 is IA minus IB, right? Remember that when we were doing mesh current, and then way back in the way back days, we had to do this superposition. There's a difference between branch currents and mesh currents, right? So I3 is it's just IB, right? So I3 is just IB. I4 is just I. Where's I4? What happened to it? Here it is. It's just IC. That's the only thing happening way over here by itself. I5, this guy, it's going to be a difference, right? You got IA going down and then IC going up through this guy, through this little branch right here. So this I5 is IA minus IC. And I6, kind of a similar situation. You've got IB going down and an IC going up. So this is IB minus IC, okay? So there's a relationship between branch and mesh currents. Okay, we can write mesh current equations now, right? So the EQs, right, there's going to be mesh current A, okay? So A, we're summing, so what do we do with mesh current? We're summing voltage terms and IZ terms. These are all resistances. The Z's are the R's. You could say IZ, you could say IR, because we're just dealing with resistance here. There's no capacitance in this model. Although in a real house there would be. Every electric motor you have in your house has inductance, and some devices have capacitance in them. Let's see. So what are we doing here? So we've got this voltage supply thing. I'm going to write it sort of solved for the voltage, but it's just a mesh current summing to 0. There's the voltage dropped across 1, 20, and 2, which is 23 IA. That's the main effect due to IA. Then you got to account for the shared 2 element, the 2 IB element. This guy, the superposition on the shared element, and then this guy, the 20 IC element. And then compare the directions. IA and IB are negative, or opposite, so this is negative. IA and IC are opposite, so this is negative. Okay, that's the first mesh current. Mesh current B. This same rise here, so it's still 120 angle 0. How do you know that these are? Oh, it's given. Yeah, it's given that these are 0. The main IB terms are 2, 40, and 1, so 43 IB. Then you've got a shared IA term, and the 40 is shared with IC. These happen to be opposite directions. Then mesh current C is going to be is 0. There's no mesh-wise. There's no voltage source in there, so this is 0. So this is 40, 50, 60, 70 IC. There's a 40 amp shared with IB, and there's a 20 amp shared with IA, and they happen to be opposite through these shared components, so there's negative signs again. Okay, there's 3 equations, 3 unknowns here. So my calculator will tell me that IA is 24 angle 0. IB is 21.96 angle 0. Skipping entering these into your calculator. As phasors, it's just these are going to be, the J components are all going to be 0. Actually, because the angles are 0, you could get away with doing this as as scalars. Yeah, that would work. You could just forget the angle 0 part, and it should work fine, because everything's 0 here. And what's bothering me is the fact that they're all 0. Like this is just at some peak. We'll just call that wherever that peak happens, we're calling it 0. And then these are really generated off of that. I mean, they're going to follow these zeros. These 0 angles are going to follow that. That is to say that the voltages that are generated here on the other side of the transformer they're generated by this signal, and assuming, neglecting the internal impedances in here, which could shift signals around. Neglecting that. Actually, let's see, that would only affect the current shift. The voltage will be in phase, because these voltages here are being generated off of this guy. They're going to be the same phase. So if this is 0, it's just an arbitrary reference starting point, then these will also be 0. So I feel better. Anyway, calculator tells me 19.40 angle 0. These are the 3 dudes. So take these. What are we solving for? Oh, take these and plug. We're finding all branch currents in the house. We want all these. Okay, plug these into this, and you get, so yields these here answers right here. So I1 is just IA, so 24 angle 0 amps, right? I2 is a 24 angle 0 minus 21.96 angle 0. It's these two, IA minus IB, which is 2.04 angle 0. I3 is 21.96 angle 0. It's just IB, and I4 is just IC, which is 19.40 angle 0. And I5 is the difference between A and C. It's these two, so it's 24 angle 0 minus 19.4 angle 0, which is 4.6 angle 0. And I6 is IB minus IC, so it's 21.96 angle 0 minus 19.4 angle 0, which is 2.55 angle 0 amps. All of these are amps. Volts, ohms, amps. All of these are amps. Okay, that's all branch currents in the house. That's the first part of this problem. Now we need to reflect these currents back across the transformer, right? We know the voltages that was given. We solve for these currents, so we know the current through these parts of the windings. This guy here is just I3 going through this part of the winding, and this part of the winding is I1, and we want to reflect those back across here and find out what IP is. So I'm going to redraw. This is because it's kind of trickish. Let's just redraw the left side of this thing again one more time. Why not? So we've got N1 windings here, and we've got IP going through this guy at the 13.2 angle 0 degrees kilovolts, this polarity. We've got a dot. Then we've got a chunk of iron in there, and then we've got a winding that's split in half, and there's N2 turns here and N2 turns here. The reason for splitting this up is it makes the solution easier. It's kind of a trick, splitting this up into two pieces. And then we could say that the winding ratio is N1 to 2 N2, because it's the number of windings on this side, colon, the number of windings on this side, and there's 2 N2 windings on this side. This is just a way of writing it that matches this diagram that makes the math a little bit easier. So, trick. So, drawing this. This is I1 phasor. This is I3 phasor. This is IP phasor. We know that if this is 120 and 120, from here we're rising 120 and we're rising another 20, so we're really rising 240 across here. So this is 240 angle 0 degrees. Then we can use the voltage turns ratio. So we have 13,200 volts on one side, and we have 240 volts on the other side. And the ends go this way. The N and 2N2 go like that. This is our from our voltage turns ratio formula. So we don't know what these ends are exactly. We don't know exactly how many turns there are on either side, but we know the ratio is that. And I'm ignoring the angles here because they're the same. They're both 0, so we can just ignore angles. We can do the same little trick with the amp turns ratio. So using our amp turns ratio formula, we have N1 IP will be, okay, another trick here. How to explain this? That you're, I'm just going to write it out. N2 I1, N2 I3. So this is a trick that is not obvious. Okay, we're right here. We're summing Ni terms. And I1 and I2 I1 and I3 are different values. It's not obvious, but it sort of makes sense if you think about it. I mean, there's a current through here, and the turns ratio is going to produce, you know, a certain current in here and a certain current in here. It doesn't it, you know, those currents will sum to IP, but it doesn't. There's nothing saying that I1 and I3 have to be the same. I mean, they're different values. Okay, and they are in a house. Depends on what the loads are. There's 20 ohms here and 40 ohms here, and there's this weirdness over here too. So, you know, these two little branch currents are not going to be the same, but they're going to sum, you know, by the time they travel the entire distance, they're going to sum. So it's not obvious, but it kind of makes sense. You got to get in, you got to jump in here somewhere on these problems. There's a lot of history involved in developing these house distribution circuits. There's a lot of weird stuff that goes on, and some of it is has to do with the way the system grew over time and the hardware that was available. And as they upgraded the system, as people used more and more power, they had to kind of make old equipment work, and we ended up with some weird stuff. This is part of that. Anyway, that's this first trick. So a couple of tricks. Anyway, we can solve now. All right. So now we're just. So I guess what I'm trying to say is that this has a physical meaning, sort of. But now we're just doing math now. So we're going to solve for IP. It's going to be, we can factor out the N2, which physically meaning-wise makes me feel weird, but it's math, and that's okay. So you can do this. You can factor out the N2s. And so N2 over N1, we already solved for that. It's 1 by 110. We solved for that because we were given the voltage ratios. And, we do have I1 and I2s. That I1 is 24. And we could throw the angles back in or not, but let's throw them back in. And I3 is 2196 angle 0. So this is 0.42 angle 0 amps. Okay, and that's this. This was an answer too, all of these dudes. And this is an answer. So that's interesting, right? That means the power pole where we're tapping, you know, we've got these A and B lines feeding many houses, right? There's another one over here, another one. There's all these houses, and each house is drawing a half amp off of the main lines, and these main lines all those half amps will add up to many amps. But so that's a reasonable result. And these are reasonable too. Look, this is 24 amps, and 20 amps, right? This is reasonable value for your house. Like if you go look in wherever your breaker box is, there's a lot of circuit breakers that are anywhere from 10 to 50 amps. So these are reasonable values for in a house. Okay, and this is a reasonable value here to pull off of the to pull off of the line, right? Because they all add up. Half amp here, half amp there, half amp everywhere. All right, so this is good. I like this stuff. You know, I like power distribution. Okay, thank you.